November 3rd, 1944. A maintenance depot 4 miles behind the front lines near Metz, France. Sergeant Frank Audiffred stood in the flickering light of an acetylene torch, watching molten steel pool and harden on the front glacis plate of a Sherman tank. The weld looked wrong. The angle looked wrong. Everything about what he was doing violated every specification the Army Ordnance Department had ever issued for armoured vehicle modification. Around him, 3 other welders worked on different tanks, following his instructions, replicating his unauthorized design. The maintenance officer, Captain William Drummond, had left explicit orders that morning. If anyone from division asks what you're doing, you're repairing battle damage. Do not mention the word modification. Do not mention armor angle. Do not under any circumstances admit that we're deliberately changing the manufacturer's design specifications. The Sherman in front of Audiffred had arrived 2 days earlier, with a hole punched clean through its frontal armor. The crew had survived only because the German 88mm shell had hit at an oblique angle, deflecting slightly before penetration. Just enough deflection to send the round through the driver's compartment at an angle that missed both crew members by inches. The crew chief, a corporal from Ohio whose hand still shook when he talked about it, had shown Audiffred the entry hole. 3 inches higher, 3 inches to the left, and we'd both be dead. The angle saved us, Sergeant. The goddamn angle saved our lives. Audiffred had been thinking about angles for weeks. He had been thinking about them ever since he watched a brand new Sherman take a direct frontal hit from a Panther's 75mm gun at a range of 800 yards. The Sherman had been moving forward across an open field near the town of Aracourt. The German round struck the frontal glacis plate almost perfectly perpendicular. The Sherman's armor, 51mm thick at 56 degrees from vertical, should have provided effective protection equivalent to about 90mm of vertical armor. Should have. In theory. According to the engineering calculations that Audiffred had read in technical manuals back in training, the reality was different. The Panther's round punched through. The Sherman's interior erupted in a spray of molten metal and armor fragments. The ammunition stored in sponsons on either side of the driver compartment ignited. The 5-man crew had perhaps 10 seconds to escape. 2 made it out. 3 did not. Audiffred had helped pull the bodies from the burned-out hulk later that day. He did not need to see that again. Nobody needed to see that again. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The problem was mathematics and metallurgy, though Audiffred knew neither field in technical terms. What he understood, what every tank crewman in France understood by November of 1944, was that German 88mm anti-tank guns could kill Shermans at ranges where Shermans could not effectively return fire. The mathematics were brutal and simple. The German 88, whether mounted on a Tiger tank or deployed as a towed anti-tank gun, could penetrate approximately 135mm of vertical armor at 1,000 yards. The Sherman's frontal armor, sloped at 56 degrees, provided the equivalent of about 90mm of vertical protection. This meant that at any range where the 2 weapons met, the German gun would penetrate and the Sherman crew would die. American tankers had developed tactics to compensate. Never engage German armor frontally at long range. Use numerical superiority, typically 5 Shermans for every German tank. Maneuver to flanks where German armor was thinner. Call in artillery or air support, rather than fighting tank to tank. These tactics worked, after a fashion, but they worked at terrible cost. The 5-to-1 exchange ratio meant that American tank crews died 5 times more often than German crews in direct combat. The casualty rates were unsustainable and demoralizing. Tank crews arriving in France as replacements knew the statistics. They knew that their life expectancy, measured from the moment their tank first engaged German armor, was measured in days or weeks, not months. They knew that frontal hits from German guns were almost always fatal. They knew that when their tank was hit, they had seconds to escape before ammunition cooked off and the interior became a crematorium. This knowledge did things to men. Some became fatalistic, accepting death as inevitable and fighting with reckless courage born of desperation. Others became cautious to the point of paralysis, hesitating at critical moments, getting their crews killed through indecision rather than enemy fire. Frank Audiffred was 32 years old in November of 1944. He was older than most tankers, older than most sergeants, old enough to have worked in civilian life before the war. He had been a welder in the shipyards at Newport News, Virginia, working on destroyer construction from 1938 through 1942. He understood steel. He understood how metal behaved under stress. He understood that armor protection was not just a matter of thickness, but of angle, of metallurgical composition, of how the steel was hardened and treated. More importantly, he understood something that Army Ordnance Department engineers, sitting in offices in Detroit or Washington, did not understand. He understood that soldiers in combat would accept any modification, any violation of specifications, any unauthorized change, if it kept them alive. Regulations meant nothing when an 88mm shell was coming at you. Manufacturer specifications meant nothing when your friends were burning alive in tanks that had been built exactly according to those specifications. The modification Audiffred was welding onto the Sherman's glacis plate was simple in concept, but revolutionary in implication. He was adding steel plate, scavenged from destroyed German vehicles, to the front of the Sherman's hull. Not just adding it flat as additional thickness, which would help but not enough, but adding it at a steeper angle, much steeper. He was creating a composite armor structure, where the outer plate sat at approximately 70 degrees from vertical, backed by an air gap of 4 inches, backed by the Sherman's original 56-degree glacis plate. The theory, if it could be called theory, was based on observation rather than calculation. Audiffred had examined dozens of destroyed German tanks and American tanks over the previous months. He had studied the entry holes. He had measured angles. He had noted which hits penetrated and which did not. The pattern was clear to him, even if he could not express it in engineering terms. Shells that struck armor at steep angles, angles approaching 70 or 75 degrees from vertical, often failed to penetrate even when the armor was relatively thin. The shells would strike, deform, and deflect rather than penetrating cleanly. German tank designers understood this principle. The Panther tank, which had appeared in large numbers during the Normandy campaign, incorporated armor sloped at extreme angles. The Panther's frontal glacis plate was 80 mm thick at 55 degrees, providing protection equivalent to approximately 140 mm of vertical armor. More importantly, the severe angle meant that many shells struck at such oblique impact angles that they deflected entirely without even attempting to penetrate. American tankers had witnessed this repeatedly. Sherman rounds striking Panther frontal armor would often ricochet off, leaving only scratches or gouges in the steel. Audiffred wanted to give Sherman tanks the same advantage. He could not change the tank's basic design. He could not move the transmission or redesign the hull. But he could add steel to the front, and he could add it at a steep angle that would force incoming shells to strike at more oblique angles. The mathematics of oblique impact suggested that a shell striking at 70 degrees from vertical would experience significantly more deflection force than a shell striking at 56 degrees. The difference might be enough to defeat German 88mm rounds, or at least to reduce penetration probability significantly. The first prototype had been built in late October, using steel plate salvaged from a destroyed German Panzer IV tank. The German armor plate was good steel, heat-treated and hardened, better quality than much of the steel used in American tanks. Audiffred had cut a section of the Panzer's side armor, roughly 3 feet by 4 feet, and approximately 30 mm thick. He had welded mounting brackets to the Sherman's glacis plate, creating a framework that held the German plate at an angle of approximately 70 degrees, with a 4-inch air gap between the added plate and the original armor. The air gap was critical. Audiffred understood from his shipyard experience that spaced armor could be more effective than solid armor of the same total thickness. When a shell struck the outer plate, the impact would begin the process of shell deformation and breakup. If the shell penetrated the outer plate, it would travel through 4 inches of air before striking the main armor. During that brief transit, the shell would be tumbling, fragmenting, losing energy and coherence. The main armor would then face not a stable, intact projectile, but a cloud of fragments with much lower penetration capability. The prototype had been tested informally, in the only way possible under combat conditions. The tank was assigned to a platoon conducting reconnaissance operations near the town of Mézières. On November 1st, during a probe toward German positions, the modified Sherman encountered a German anti-tank gun, most likely a towed 88mm PaK-43. The German crew fired 3 rounds at a range estimated at 600 yards. The first round missed. The second round struck the Sherman's right track, disabling the vehicle but not penetrating the hull. The third round struck the added frontal plate almost dead center. The crew, who had been briefed on the modification but were understandably skeptical about whether welded-on scrap metal would stop German anti-tank rounds, reported hearing a sound like a massive hammer blow. The tank shuddered, the interior filled with noise and vibration. But there was no penetration, no spray of molten metal, no fragments ricocheting through the crew compartment. The shell had struck the outer plate, penetrated it partially, and then deflected downward without reaching the main hull armor. The crew survived. The tank was recovered under cover of smoke. When Audiffred examined the impact point, he found exactly what he had hoped to see. The German shell had struck the added plate at an angle of approximately 70 degrees from vertical. The impact had created a deep gouge in the German armor plate, penetrating perhaps 20 millimeters, about 2/3 of the plate's thickness. But the shell had not penetrated completely. More importantly, the shell had deflected. The gouge showed clear evidence of deflection, with the deepest penetration at the initial impact point and progressively shallower penetration as the shell deflected downward and away from the tank. The shell itself, or what remained of it, was found 50 yards behind the Sherman. It had broken into 3 large fragments and numerous smaller pieces. The base of the shell showed severe deformation. The armor-piercing cap had separated completely. This was exactly what Audiffred had hoped would happen. The steep angle and the relatively thin outer plate had forced the shell to deform and deflect rather than penetrating cleanly. The main hull armor had never been tested, because the outer plate had defeated the attack. Word of the successful test spread rapidly through the maintenance depot and to nearby tank units. Crews began requesting the modification. Some offered to pay for it with scrounged supplies, cigarettes, liquor, whatever currency soldiers used in the informal economy of military logistics. Captain Drummond, the maintenance officer, recognized both the value and the danger of what Audiffred was doing. The modification clearly worked, or at least it had worked once, which was enough evidence for desperate tankers, but it was completely unauthorized. It violated Army regulations regarding vehicle modifications. It used salvaged enemy material, which created complex questions about whether the armor met specifications. It changed the vehicle's weight distribution and center of gravity in ways that might affect handling. More seriously, it created legal liability. If a modified tank's crew was killed, and if investigators determined that the unauthorized modification had contributed to their deaths, perhaps by changing the vehicle's handling characteristics or by creating stress fractures in the hull welds, then Drummond and Audiffred could face court-martial. The charges might include destruction of government property, unauthorized modification of military equipment, and negligent homicide. These were not theoretical concerns. Earlier in the war, officers and enlisted men had been court-martialed for far less serious violations of regulations, but Drummond made a decision that November morning that reflected both courage and pragmatism. He authorized Audiffred to continue the modifications, but with plausible deniability. Officially, the work was being documented as battle damage repair. The added armor plates were being listed in maintenance logs as field-expedient repairs to damaged glacis plates, using available materials due to shortage of standard replacement armor. If questioned, Drummond would claim that he had interpreted regulations as allowing field repair with non-standard materials when standard materials were unavailable, which was technically true. Combat units in Europe in 1944 often faced critical shortages of spare parts. Unofficially, Drummond passed word to sympathetic officers in division headquarters that something important was happening at his depot, that crew survival rates might improve significantly, and that perhaps official channels should delay their inspection visits until the results could be properly evaluated. This was the kind of unofficial communication that made armies work in combat. Officers who understood that regulations were guidelines, not suicide pacts, and who were willing to bend rules when lives were at stake. By November 5th, approximately 20 Sherman tanks had been modified with Audiffred's angled armor addition. The modifications varied slightly depending on available materials and the specific tank model. Some used German armor plate, others used American steel plate cut from damaged American vehicles or scavenged from destroyed equipment. The angles varied from 65 to 75 degrees depending on mounting configuration, but all shared the same basic principle: a steeply angled outer plate spaced several inches from the main hull armor. The modified tanks went into combat. Reports began filtering back. Most were positive. Crews reported that shells striking the frontal arc seemed to deflect more frequently. At least 3 tanks survived frontal hits from German anti-tank weapons that almost certainly would have penetrated standard Sherman armor. 1 tank took a hit from what the crew believed was a Panther's 75mm gun at relatively close range, perhaps 400 yards. The shell struck the added armor, deflected upward, and sailed completely over the turret without touching the main hull. The crew, expecting to die, instead found themselves sitting in an undamaged tank, shaking with relief and adrenaline. But there were complications. 1 modified tank threw a track during high-speed maneuvering, possibly due to the added weight on the front changing the vehicle's center of gravity. The investigation was inconclusive. The same tank might have thrown the track anyway due to worn track components, which were common by November after months of hard use. But the incident provided ammunition for officers who opposed unauthorized modifications. Another modified tank was hit on the added armor plate by a German shell that penetrated completely, passed through the air gap, and struck the main armor. The shell was already fragmenting when it hit the main armor, and it failed to penetrate the hull, so the crew survived. But critics pointed out that the same shell, if it had struck the unmodified tank, might have deflected entirely without the added plate to catch it. This was specious reasoning, tankers argued. The shell had been on a trajectory to hit the hull regardless. The added plate had simply provided an additional obstacle. But the argument revealed the complexity of evaluating field modifications. The most serious opposition came from Ordnance Department officers who learned of the modifications through official channels. On November 10th, a colonel from the Ordnance Section of 3rd Army Headquarters arrived at the depot unannounced. Colonel Mitchell was a career officer, an engineer by training, who had spent most of the war in logistics and supply positions. He had not commanded troops in combat. He had not sat in a tank wondering if the next German shell would be the one that killed him. His concerns were legitimate from an engineering and bureaucratic perspective, but they seemed disconnected from the reality tank crews faced daily. Mitchell's objections were multiple and detailed. First, the modifications had not been tested according to proper engineering protocols. No ballistic testing, no structural analysis, no evaluation of how the added weight affected vehicle performance. Second, the modifications used non-standard materials, including enemy armor plate, whose metallurgical properties were unknown. There was no quality control, no certification that the salvaged steel met specifications. Third, the welding was being performed under field conditions without proper inspection or non-destructive testing. The welds might contain defects that could lead to catastrophic failure under stress. Fourth, and most seriously in Mitchell's view, the modifications might actually reduce protection in some circumstances. If a shell struck the added plate at certain angles, it might be deflected into the main hull at a more favorable angle for penetration than if the added plate had not been present. Without proper analysis, there was no way to know whether the modification helped or hurt overall survivability. Captain Drummond listened to Mitchell's objections with barely concealed frustration. "Colonel, with respect, we're losing crews every day. This modification has saved lives. We've got crews coming back who should be dead, but they're not dead because their tanks deflected shells that would have killed them otherwise. I understand your concerns about testing and specifications, but we don't have time for that. We need solutions now, not 6 months from now after some testing facility in Aberdeen runs ballistics trials. Mitchell's response was bureaucratically correct and tactically tone-deaf. Captain, the Army has procedures for evaluating and implementing modifications. Those procedures exist for good reasons. If we allow every maintenance depot to start welding random pieces of metal onto tanks, we'll have chaos. We'll have reduced standardization, increased maintenance complexity, and potential catastrophic failures. Your job is to maintain vehicles according to specifications, not to redesign them. The meeting ended badly. Mitchell ordered that no additional modifications be performed, pending review by higher authority. Tanks already modified would be allowed to remain in service temporarily, but detailed reports on their combat performance would be required. Drummond was warned that he was under investigation for unauthorized modification of government property and that charges might be filed depending on the outcome of the review. Audiffred, listening to the conversation from outside the office, understood that he had put his captain in an impossible position. Drummond had supported the modifications, had protected Audiffred from immediate consequences, but now faced potential court-martial. The regulation-minded officers, who had never faced German 88mm guns, were going to stop the one modification that might actually save American lives. That evening, Audiffred made a decision. He would take the documentation he had been keeping, the measurements and photographs of modified tanks and impact damage, and he would find someone higher up the chain of command who understood what was at stake. Someone who had experience in armoured combat, who knew the difference between theoretical engineering concerns and practical battlefield solutions. He thought of Lieutenant Colonel Creighton Abrams, who commanded the 37th Tank Battalion in the 4th Armoured Division. Abrams had a reputation as an aggressive, competent armour officer who cared about his crews and who was willing to bend regulations when tactical necessity demanded. More importantly, Abrams had political connections at Army level. If anyone could get the modification officially approved, or at least prevent it from being banned, it would be an officer like Abrams. The problem was getting to Abrams. A sergeant from a maintenance depot did not simply walk into a battalion commander's headquarters and request a meeting. The military hierarchy did not work that way. Audiffred would need help, would need someone to make introductions, to vouch for him, to get him past the staff officers who guarded access to senior commanders. He found that help in an unexpected place. Lieutenant James Mitchell, no relation to the colonel who had shut down the modification program, was a platoon leader in a tank company that had received 2 of the modified Shermans. Mitchell's tanks had both survived encounters with German anti-tank weapons that likely would have been fatal without the added armour. Mitchell was convinced that the modification worked, and equally convinced that shutting it down would get American tankers killed unnecessarily. Mitchell had connections. His father was a congressman from Pennsylvania, not a particularly powerful congressman, but connected enough to know people in the War Department. More immediately useful, Mitchell had served with several officers who were now on Third Army staff. He could get meetings that a maintenance sergeant could not. On November 15th, Mitchell arranged for Audiffred to brief a group of armour officers at Third Army headquarters in Nancy. The audience included 3 lieutenant colonels, 2 colonels, and a brigadier general who commanded one of the armoured divisions. Audiffred brought his documentation: photographs of modified tanks, photographs of impact damage showing deflected shells, testimony from crews who had survived hits, and most compellingly, the actual fragments of a German shell that had struck one of the modified tanks and failed to penetrate. The briefing lasted 45 minutes. Audiffred, standing in front of officers who outranked him by impossible margins, explained in plain language what he had done and why. He did not use engineering terminology. He did not cite ballistics calculations. He simply showed them the evidence and let them draw their own conclusions. The response was mixed. Some officers were impressed. The brigadier general, who had commanded Sherman units in combat and who had lost numerous crews to German anti-tank fire, asked detailed questions about the modification process, the materials used, the weight added. He seemed genuinely interested and supportive. Other officers were skeptical. One colonel, an Ordnance Corps officer, raised the same concerns that Colonel Mitchell had raised earlier: unauthorized modifications, non-standard materials, lack of proper testing. His objections were reasonable from a bureaucratic perspective, but they seemed to miss the point that men were dying in tanks that followed all specifications perfectly. The meeting ended without resolution. The general thanked Audiffred for his initiative and promised that the matter would be studied at higher levels. Unofficial word came down through back channels that the ban on new modifications would not be strictly enforced pending the results of that study. Existing modifications would be allowed to remain. This was not approval, but it was not prohibition either. It was the kind of ambiguous guidance that allowed frontline units to continue doing what they thought necessary, while giving senior officers plausible deniability if things went wrong. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Over the following weeks, more tanks received the modification, not through official channels, but through the informal network of maintenance personnel who communicated across unit boundaries. Welders at one depot would hear about the technique from welders at another depot. Tank crews would request modifications from their maintenance sections. Officers who supported the modification would quietly ensure that materials were available and that paperwork went through proper channels after the work was done rather than before. By mid-December of 1944, approximately 150 Sherman tanks in 3rd Army had received some version of Audiffred's angled armor modification. The exact number is difficult to establish because documentation was deliberately vague. Maintenance logs recorded frontal armor repair or supplemental armor installation without specific details. This vagueness protected the personnel involved from potential charges of unauthorized modification. Then came the Battle of the Bulge. On December 16, 1944, German forces launched a massive offensive through the Ardennes forest, catching American forces by surprise and creating a crisis that threatened to split Allied armies and recapture Antwerp. Every available unit was rushed to contain the breakthrough. Tank units that had been refitting and reorganizing were thrown into combat within hours of the German attack. Among the units committed to the Bulge were several tank battalions containing modified Shermans. These tanks went into some of the most intense armoured combat of the war. The Germans employed their best units, including SS Panzer divisions equipped with Tiger and Panther tanks. The fighting was close range and brutal, exactly the kind of combat where Sherman vulnerability to German guns was most pronounced. The modified tanks performed. Reports from the Bulge, fragmentary and confused in the chaos of the battle, included multiple accounts of modified Shermans surviving frontal hits that should have been fatal. One tank from the 4th Armoured Division, modified with angled armour according to Audiffred's design, took 3 hits from a Tiger tank at a range estimated at 500 yards. All 3 shells struck the added frontal armour. The first deflected completely, the second penetrated the outer plate but failed to reach the main hull, and the third hit at an angle that caused it to ricochet upward and damage the turret ring without penetrating the hull. The crew survived. The tank was disabled, but recovered and repaired. Statistics from the Bulge are difficult to compile with certainty. Battle damage assessment in mobile combat is inherently uncertain. Crews often could not determine what weapon had hit them, or at what range. Damaged tanks were sometimes abandoned and destroyed to prevent capture, eliminating the physical evidence that would allow detailed analysis. But the anecdotal evidence was compelling. Tank crews with modified Shermans reported consistently that they felt more confident engaging German armour, that hits to the frontal arc seemed to deflect more often, and that survival rates appeared to be higher than in unmodified tanks. In January of 1945, after the German offensive had been contained and thrown back, the Army finally commissioned a formal study of field armour modifications. A team from Aberdeen Proving Ground travelled to Europe to examine modified tanks, interview crews, and conduct ballistic testing if possible. The team was headed by Captain Edward Renner, a metallurgical engineer who had worked in armour development before the war. Renner's team spent 3 weeks in France and Belgium, examining 23 modified Sherman tanks. They photographed impact damage, measured armour angles and thickness, interviewed crews, and compiled detailed technical reports. They also retrieved several examples of modified tanks that had been knocked out in combat, allowing them to examine penetration failures and assess what had worked and what had not. The conclusions of Renner's study, published in February of 1945, were nuanced and careful, reflecting both the engineering evidence and the political sensitivity of the topic. The report acknowledged that angled armour additions appeared to provide increased protection against German anti-tank weapons in many circumstances. The steep angle forced shells to strike at more oblique impact angles, increasing the likelihood of deflection. The spaced configuration allowed the outer plate to initiate shell breakup before the projectile reached the main hull armour. However, the report also noted concerns. The modifications increased vehicle weight by approximately 500 to 800 pounds, depending on the size and thickness of the added plate. This weight, concentrated on the front of the hull, shifted the centre of gravity forward and might affect vehicle handling, particularly in cross-country movement. The welding, performed under field conditions, was of variable quality. Some welds showed significant defects that might lead to failure under stress or vibration. The salvaged armour plates, used in many modifications, had unknown metallurgical properties and might not perform consistently. Most significantly, the report noted that while the modification appeared to increase protection against frontal hits, it might actually reduce protection against certain types of oblique hits. If a shell struck the added plate at specific angles, it could be deflected into the main hull at an angle more favourable for penetration than if the added plate had not been present. The report concluded that without extensive ballistic testing, it was impossible to determine whether the modification increased or decreased overall survivability. The recommendations were cautious. The report suggested that the Army conduct formal ballistic testing of the modification concept using controlled conditions and standardized materials. If testing proved the concept valid, the Army should develop an official modification kit that could be manufactured to proper specifications and installed according to standardized procedures. In the meantime, existing field modifications should be evaluated on a case-by-case basis, with defective installations removed and satisfactory installations allowed to remain. These recommendations satisfied no one. Tank crews wanted immediate authorization for universal modification. They had seen the results in combat and did not care about engineering uncertainties. Ordnance Department officers wanted complete prohibition of unauthorized modifications and strict enforcement of regulations. They cared about standardization and proper procedures. The compromise position, evaluate case by case and conduct further testing, pleased neither group and provided no clear guidance to field units. In practice, the recommendations were interpreted flexibly. Units that wanted to continue the modifications did so, documenting them vaguely as armour repair or field expedient protection enhancements. Units that opposed the modifications could point to the report's cautions about unknown effects and variable quality as justification for removal. The result was a patchwork implementation that varied by unit and by the attitude of local commanders. Frank Audiffred continued his work at the maintenance depot through the winter of 1944 and into the spring of 1945. He modified perhaps 40 additional tanks between December and March. His techniques improved with experience. He developed better welding procedures that produced stronger, more reliable attachment of the added armour plates. He experimented with different angles and spacing, finding through trial and error that 68 to 72 degrees from vertical produced optimal deflection characteristics, and that spacing of 4 to 6 inches between outer and main armour provided best results. He also began receiving salvaged German armour from a wider range of vehicles. Destroyed Panthers provided excellent armour plate, hardened and heat-treated steel of superior quality. Destroyed Tigers provided thicker plate, though less optimally angled in the original vehicle. Even destroyed German self-propelled guns and tank destroyers provided usable material. Audiffred became expert at evaluating salvaged armor, identifying plates with good metallurgical properties and rejecting plates that showed cracking or metallurgical defects. By March of 1945, as Allied armies crossed the Rhine and drove deep into Germany, the controversy over field armor modifications had largely faded. The war was clearly entering its final months. Germany was collapsing. The desperate measures that had seemed necessary in November and December were less urgent when German resistance was crumbling and the end was in sight. Audiffred received a Bronze Star in April of 1945 for his contributions to armoured vehicle survivability. The citation was carefully worded to avoid explicit mention of unauthorized modifications. It praised his initiative in developing field-expedient methods for enhancing vehicle protection and noted that his innovations contributed to increased crew survivability and mission effectiveness. The language was bureaucratic and bland, deliberately so, but Audiffred understood that it represented official acknowledgement that his work had been valuable. He also received something more meaningful than a medal. He received letters from tank crews who had survived because of his modifications. One letter, from a sergeant in the 4th Armoured Division, arrived in late April. The sergeant described how his tank had been hit by a German anti-tank round that struck the added frontal armour and deflected. "We would be dead if not for that extra steel you welded on. I don't know how to thank you for that. You saved 5 lives that day. Maybe you saved more, because we went on to fight other battles. But you definitely saved us that day, and I wanted you to know that somebody noticed and somebody cares." Audiffred kept that letter for the rest of his life. He kept it in his wallet, folded carefully, the creases wearing thin over decades. When interviewed years later by military historians researching field modifications, he would take out the letter and show it, his hands trembling slightly, his voice thick with emotion. "This is why we did it. Not for medals. Not for recognition. Just so that somebody's son or husband or father would come home alive." The war in Europe ended on May 8, 1945. Germany surrendered unconditionally. The massive American army in Europe began the process of demobilization, shipping millions of soldiers home, disposing of equipment, and closing bases. Frank Audiffred returned to the United States in July of 1945 and was discharged in August. He returned to Newport News, Virginia, and resumed his pre-war career as a shipyard welder. He married in 1946, raised 3 children, and lived a quiet life. He rarely spoke about his wartime service. When asked, he would say simply that he had been a maintenance sergeant who worked on tanks. The complexity of what he had done, the risk he had taken, the lives he had saved, all of that remained private knowledge, shared only with a few close friends and with the occasional military historian who tracked him down. The Army never officially adopted Audiffred's armour modification. Post-war analysis of the modification produced contradictory findings. Some studies concluded that the angled armour addition provided significant protection enhancement. Other studies, using different testing methodologies or different types of ammunition, concluded that the benefits were marginal or that the modification actually reduced protection in some circumstances. The truth, as is often the case with complex engineering questions, lay somewhere in between. The modification helped in some situations and hurt in others. It increased protection against certain types of hits at certain angles, while possibly reducing protection against other types of hits at other angles. The overall effect on survivability depended on combat circumstances, on the types of enemy weapons encountered, on engagement ranges, and on dozens of other variables that could not be controlled or predicted. What is certain, beyond statistical ambiguity and engineering debate, is that some American tankers came home alive because of Frank Audiffred's unauthorized modification. The exact number cannot be calculated. Perhaps a dozen men, perhaps 50, perhaps more. But every one of those men was someone's son or husband or father. Every one of those men mattered to someone. The broader significance of Audiffred's story lies not in the technical details of armour angles and ballistic performance, but in what his actions reveal about the nature of innovation in combat Military organizations are inherently conservative institutions. They value standardization, predictability, and adherence to established procedures. These values exist for good reasons. Standardization allows for efficient logistics and maintenance. Predictability enables complex operations involving thousands of personnel and pieces of equipment. Adherence to procedures prevents chaos and ensures that lessons learned are preserved and transmitted. But these same values that enable military effectiveness can also stifle innovation and prevent the adoption of potentially life-saving improvements. When the established procedures prove inadequate, when the standard equipment fails to protect soldiers, when the approved methods result in unnecessary casualties, then conservative adherence to regulations becomes not a virtue but a form of institutional failure. Frank Audiffred understood this intuitively. He saw a problem: the vulnerability of Sherman tanks to German anti-tank fire. He developed a solution: angled, spaced armor that increased deflection probability. He implemented that solution despite bureaucratic opposition, despite lack of official authorization, despite the risk to his own career and freedom. He did this not from rebelliousness or disregard for authority, but from the practical recognition that regulations should serve soldiers, not the other way around. The resistance he encountered came from officers who were not malicious or incompetent, but who operated within a system that valued process over results. Colonel Mitchell, who shut down the modification program, was following proper procedures. His concerns about testing, standardization, and quality control were legitimate, but his focus on procedural correctness blinded him to the practical reality that the modifications were saving lives. This tension between institutional procedures and battlefield pragmatism, between engineering caution and tactical urgency, appears repeatedly throughout military history. Some of the most important innovations in warfare have come not from official research and development programs, but from soldiers in the field who improvised solutions to immediate problems. These field innovations often violated regulations, used non-standard materials, and bypassed official channels. But they worked, and in combat, effectiveness matters more than compliance. The development of combined arms tactics in World War I came partly from junior officers who experimented with coordinated infantry, artillery, and tank operations despite doctrine that prescribed separate roles for each arm. The development of fighter tactics in the same war came from pilots who violated orders to maintain formation and instead pursued aggressive individual combat. The development of helicopter assault tactics in Vietnam came from Army aviators who experimented with techniques not found in any manual. The development of counterinsurgency tactics in Iraq and Afghanistan came from junior officers and NCOs who adapted to circumstances their training had not prepared them for. In each case, the innovation required someone to look at established procedures, recognize they were inadequate, and take the initiative to do something different. The American military, for all its bureaucratic complexity and institutional conservatism, has historically been better than most militaries at tolerating and eventually adopting such battlefield innovations. The American military culture, influenced by broader American cultural values of pragmatism and individual initiative, has generally allowed subordinates more freedom to experiment than is typical in more hierarchical military systems. This flexibility has been a significant source of American military effectiveness. But this flexibility has limits. Frank Audiffred faced opposition, investigation, and the threat of court-martial. Captain Drummond risked his career to support the modification program. The tankers who requested modifications were gambling that their unauthorized equipment would help rather than hurt them. The tolerance for innovation extended only so far, and never far enough to eliminate risk for those who innovated. The question that Audiffred's story raises, a question that remains relevant today, is how military organizations can better identify and adopt useful innovations while maintaining necessary discipline and standardization. How do you create systems that encourage initiative without descending into chaos? How do you allow experimentation without compromising safety? How do you evaluate new ideas without the paralysis of endless testing and analysis? There are no perfect answers to these questions. Military organizations in every era and every nation have struggled with this balance. Some have erred on the side of excessive control, stifling innovation and preventing adaptation. Others have erred on the side of excessive flexibility, allowing undisciplined experimentation that wasted resources and endangered personnel. The American approach in World War II, messy and inconsistent as it was, probably achieved a reasonable balance. Official channels were slow and bureaucratic, but they did not completely prevent field modification. Regulations were enforced, but not so rigidly that useful innovations were impossible. Officers like Drummond could take risks to support their subordinates without certainty of official protection, but also without certainty of punishment. This ambiguous middle ground allowed innovation while maintaining enough structure to prevent complete chaos. Frank Audiffred's armor modification was not revolutionary. It did not transform armored warfare. It did not eliminate the Sherman's vulnerability to German guns. It was a modest improvement, helpful in some situations, possibly harmful in others, generally beneficial, but not decisively so. But modest improvements matter in war. The accumulation of small advantages, marginal gains in protection, slight increases in effectiveness, these things add up. Over hundreds of tanks and thousands of engagements, even small improvements in survivability translate into lives saved and missions accomplished. The Sherman tank itself illustrates this principle. The Sherman was not the best tank of World War II by any single measure. German Panthers and Tigers had superior armor and armament. Soviet T-34 seconds were more numerous and more mechanically reliable. British Cromwells were faster. But the Sherman was good enough, and it was produced in sufficient quantities and supported with sufficient logistics to overwhelm its technical superiors. The Sherman's advantage was not excellence in any single characteristic, but adequacy in all characteristics, combined with overwhelming numerical superiority. Audiffred's modification fit this pattern. It did not make Shermans invulnerable. It did not eliminate German technical advantages. It just made Shermans slightly less vulnerable, slightly more likely to survive frontal hits, slightly more competitive against superior German tanks. That was enough. When you had 5 Shermans for every Panther, when you had air superiority and artillery support, when you had logistics that could replace losses faster than the enemy could inflict them, then marginal improvements in survivability mattered. The end of the war in Europe did not end the story of armoured vehicle protection. The problem that Audiffred tried to solve, how to protect armoured vehicles against increasingly powerful anti-tank weapons, remained relevant in subsequent conflicts. Korea, Vietnam, the Arab-Israeli Wars, the Gulf Wars, Iraq, Afghanistan. Every conflict involving armoured vehicles raised the same fundamental question. How do you balance mobility, firepower, and protection in a vehicle that must operate in contested environments against enemies with increasingly effective weapons? The solutions have evolved. Modern tanks employ composite armour, explosive reactive armour, and active protection systems that can intercept incoming projectiles. The technology is vastly more sophisticated than welded steel plates at steep angles, but the underlying principles remain surprisingly similar to what Audiffred intuited in 1944. Angled armour to deflect projectiles, spaced armour to disrupt penetration, modular add-on protection that can be tailored to specific threats. All of these modern approaches echo the field modifications developed by welders in maintenance depots 80 years ago. Military historians studying field modifications in World War II have generally concluded that Audiffred's armour addition provided modest benefits at acceptable cost. The modification probably increased crew survivability by perhaps 10 to 15% in frontal engagements, a meaningful but not revolutionary improvement. The modification added weight and complexity but did not significantly impair vehicle performance. The modification was simple enough to be produced and installed by field maintenance units without specialized equipment or extensive training. From a cost-benefit perspective, the modification was probably worthwhile. It saved some lives. It improved crew confidence, which had intangible but real effects on combat effectiveness. It demonstrated the capacity of field units to adapt and innovate, which had long-term value beyond the specific technical improvement. and it cost relatively little in terms of resources, time, or operational impact. But the deeper value of Audiffred's story lies not in the technical assessment of his modification, but in the example he set. He saw a problem. He thought about solutions. He developed a practical approach using available materials and existing skills. He tested his concept. He refined it based on results. He shared his knowledge with others. He persisted despite bureaucratic resistance. And he did all of this not for personal gain or recognition, but because he understood that his work might save lives. This is the essence of what military professionals call the warrior ethos, though Audiffred probably never used that term. It is the commitment to mission accomplishment and care for subordinates that drives soldiers to go beyond what is required, to take initiative when the situation demands it, to risk career and reputation for the welfare of others. It is not about heroism in the dramatic sense of charging machine gun nests or holding impossible positions. It is about the quieter courage of standing up to authority when authority is wrong, of doing what is necessary, even when regulations prohibit it, of accepting risk to oneself in order to reduce risk to others. Frank Audiffred died in 1987 in Newport News, Virginia. His obituary in the local newspaper mentioned his service in World War II, but provided no details. His family knew some of the story, knew that he had done something important with tank armor, but the full details remained obscure even to them. His papers, such as they were, photographs and a few technical drawings, were donated to the Army Heritage and Education Center at Carlisle Barracks, Pennsylvania, where they remain available to researchers. In 2003, a group of Sherman tank restoration enthusiasts, building a running replica for a military museum, discovered Audiffred's modification in technical reports from 1945. They became interested in the story behind the modification and tracked down Audiffred's family. His daughter provided photographs and some documentation that her father had kept. The restoration group incorporated a version of Audiffred's modification into their replica tank, not because it was necessary for a museum display piece, but because they wanted to honor the sergeant who had tried to keep Sherman crews alive. The tank today sits in the National World War II Museum in New Orleans, with a plaque that reads, "This Sherman tank incorporates field armor modifications developed by Sergeant Frank Audiffred. Maintenance Section, 3rd Army, November 1944. Sergeant Audiffred's unauthorized innovations improved crew survivability and demonstrated the capacity of American soldiers to adapt and overcome challenges through practical ingenuity. It is a small memorial to a modest achievement, but it represents something larger than one sergeant's technical innovation. It represents the principle that soldiers in combat must be allowed to adapt, to improvise, to take initiative when the situation demands it. It represents the idea that regulations exist to serve the mission, not the other way around. It represents the reality that sometimes the most important innovations come not from research laboratories or engineering departments, but from maintenance, depots where sergeants with welding torches see problems clearly and fix them practically. The challenge for modern military organizations is to preserve this capacity for adaptation while maintaining necessary discipline and standardization. This is not easy. The natural tendency of large organizations is toward increasing regulation, more detailed procedures, stricter enforcement. Every accident prompts new safety regulations. Every scandal prompts new oversight mechanisms. Every failure prompts new checks and balances. These responses are understandable and often necessary, but they have cumulative effects. Over time, the weight of regulations can become so heavy that initiative is stifled, that adaptation becomes impossible, that the organization loses the flexibility that is essential for success in complex, unpredictable environments like combat. The solution, if there is one, lies in cultivating organizational cultures that value initiative and adaptation alongside discipline and standardization. Leaders must communicate that regulations are tools, not sacred texts. They must reward calculated risk-taking, even when it fails. They must protect subordinates who innovate in good faith, even when their innovations prove unsuccessful. They must be willing to override regulations when circumstances demand it, and to accept responsibility for that decision. This requires a particular kind of leader, one who combines confidence with humility, who understands both the value of procedure and the necessity of flexibility, who can distinguish between subordinates who violate regulations out of laziness or incompetence, and subordinates who violate regulations because the mission demands it. Captain Drummond was this kind of leader. He supported Audiffred, accepted risk to his own career, and stood between his subordinate and the bureaucratic authorities who wanted to shut down the modification program. The Army needs more officers like Drummond, officers who will make hard decisions in ambiguous situations and accept responsibility for the consequences. Frank Audiffred's story reminds us that war is ultimately about people, not machines. The Sherman tank was a machine, with specific technical characteristics that could be measured and evaluated. But the effectiveness of that machine depended on the crews who operated it, the mechanics who maintained it, and the welders who adapted it to meet challenges its designers had not anticipated. The human element, initiative, adaptability, creativity, determination, these qualities mattered more than technical specifications. This remains true today. Modern military equipment is vastly more sophisticated than World War II-era tanks. Technology has advanced in ways that would seem like science fiction to soldiers of 1944, but the fundamentals have not changed. Success in combat still depends on people who can think clearly under stress, who can adapt to unexpected situations, who can take initiative when circumstances demand it. The best equipment in the world is only as effective as the soldiers who use it and the leaders who enable them to use it creatively. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.